Okay, good after. Yep. Good afternoon, everybody. Can you hear me?
I can hear you.
Loud and clear.
Loud and clear. Okay. This doesn't seem to work today, so we'll do it like this. And can you also see the slides?
Yeah, we can see those too.
Okay, great. So before we start, for the biomedical optics course, the schedule is finally finished. You can see it. You can see it in the grid here, and also with the affiliated teachers. So after this week, or actually starting from today, you will be having a lot of different instructors that are going to tell you about the clinical applications of biomedical optics. For the light tissue interaction course, it is not quite finished yet. So I've filled in at least most of the topics that I want to discuss, but the teachers may vary a little bit even further. But I will put this schedule on Canvas as well, and update it as much as possible. So the schedule for today is hybrid because in the first part I want to finish the discussion about Monte Carlo simulations that we started last Friday, and then so let's say that takes until about 3 o'clock, and then from 3:30, Johannes de Boer is going to take over and talk to you about Raman spectroscopy. I've scheduled a long break between that because these are two very different topics. So just not to overflow you with all that information, I think we should have a little bit of a longer break in between. So my goal for now is to talk about Monte Carlo, the rest of Monte Carlo, until about 3 o'clock, and then at 15:30, Johannes will take over and talk about Raman spectroscopy. So traditional. In this case, I wanted to keep it a little bit short because some of the questions are repeat and some of the questions relate to the documents. Can you quickly, and again, do it together via the chat, discuss these questions? Pepijn asks, is today directed? Yeah, today and also Friday is still directed to both courses, and then from next week on we're going to split. So then biomedical optics is going to be on Monday and Wednesday, and light tissue interaction will stay on Tuesdays and Fridays. But this week is the last week that we still do together. Yeah, exactly, Sharon. Yeah, correct, Flat. So what was G again? No, let me answer by chat. That is. Okay, guys. You're correct. It's not always easy to get. Oh, here's Pepijn. Yeah, less than equal to a certain value. That is absolutely correct. I want to have a quick answer if somebody has for the last question, and then I'm going to move on. So if you know a certain probability density function, so to borrow the phrase, if you know the likelihood that the random variable will take a certain value, can you do you know what the expectation value is, and do you know how to calculate it? Do you know other words for the expectation value? Absolutely, that is certainly correct. So what are you calculating then?
So you're calculating the first moments of the probability density function, if I'm remembering correctly.
Yeah, that is absolutely true. And it also represents the mean value. So the weighted mean, the average, basically. Okay, so let's leave the questions now here, and because we have to make it until 3 o'clock. Okay, so what I want to talk about today again
before you move
about
on,
Carlo simulations and yeah, again the improbable journey of detected photons. A little bit of a title that I borrowed from one of our PhD students. The idea is that oh, there's somebody joining in. 1 second.
Yeah, before you move on, could you maybe quickly go over the PDF and CDF so we're all on one sure of what
I have them in the next few slides. So very quickly, the probability density function tells you how likely it is that the value falls between px, p of x, and p of x plus dx. So in a certain interval. Px of itself, therefore, has a unit. If you want to calculate the probability of something happening, so the probability itself has no units. That is just a number. Probability is 10% or 15%. But you calculate the probability of something happening in an interval, which is going to be px times dx, which means that the probability density, p of x, the function itself, is going to have a unit. So if you want to calculate the probability of absorption per meter, for example, so px is going to be something per meter, and then px times an interval dx is the probability that absorption will happen in that small interval, and that will be unitless. That will be just a pure number, a probability. And then the CDF, the cumulative distribution function, or the integrated probability, if you want, is the likelihood, the probability that something happens between in a larger interval. So you're now taking px dx, and you're going to integrate that over an interval, let's say from 0 to some value. So it's then the probability that that the event happens between 0 and some kind of end value. I have more examples in the slides. So if that is good enough for now, then I want to continue. If it's not good enough, then I'll try again.
Thanks. For me, it's clear now.
Yeah, it holds true for, yeah, that's a good question, Pepijn. Yeah, but you have to write it in discrete form then, but that is possible, and then it holds. Actually, one of my examples is discrete, so we'll get to that in a moment. So a couple of yeah, you'll hold yours. It's very good. So a couple of remarks before we started it. So what I want to do now is basically model how photons propagate in tissue. And the idea is to not to just track one photon or track the path of one photon into the tissue, but track multiple paths, so that if we do that again and again and again, we can get some kind of indication of how the actual signal in the measurement would look like. the way we do that now is that we let completely loose the idea that there are electric fields or that interference effects could occur. So photopropagation here is really just as kind of a great game of pinball, where photons are like billiard balls that bounce off particles that are also billiard balls. So you just get a certain trajectory of light through some collection of particles that cause the redirection, that cause the scattering. And then the idea is that you can calculate, or we can calculate, the probabilities of each of the sub-events in such a path. So in the illustration, you see a photon that is entering the tissue on the left hand, and it propagates to particle number 1. There it is scattered. Then it propagates to particle number 2, where it is scattered again to particle 3, 4, etc., etc., etc. So the goal is now to calculate the probabilities of each of these steps. So the probability of traveling from the point of injection to particle number 1 without anything happening. Then the probability of changing direction from the input direction to the scattered direction when it is scattered from particle 1. Then the probability of scattering of traveling to particle number 2 without anything happening. Then the probability of scattering from that direction into the new direction towards particle 3, etc., etc. So we're going to. The idea is to calculate calculate or sample the probabilities of each of these propagation steps. And because so that's what we're going to do next. And this means because we really consider this just particles colliding and bouncing off other particles, that there is no electric field, no phase information, so we're just looking in a power/intensity framework. A photon, such a particle, such a billiard ball, just represents a certain amount of energy, some of which it can drop and or not, and then it travels through the tissue. So let's look a little bit closer to what the probability of a detected signal actually is. This one by now should be familiar. This is again that cuvette with an absorbing substance in it. We shine light from one side with a known intensity I0. The cuvette has length L, and we measure the intensity on the other side, I, and we know that the ratio of I and I0, the outgoing and the incoming, is given by Lambert-Beer's law, exponential minus the absorption coefficient times the length of the cuvette. Okay, so now let's say this is, if you would calculate this for a given geometry, that is 0.01, for example. If we want to now look, look at this into this picture of photons as billiard balls that collide or that disappear, that would mean that if this efficiency is, if this fraction of transmission I over I0 is 0.01, that would mean that 1 out of 100 of these photons, of these billiard balls that you sent into this cuvette would be transmitted to the detector and would be measured, and that 99 of them would be somehow absorbed somewhere in between, just disappear. So that means that if you calculate by some statistical means the total probability of transmission for this experiment, it is going to be a good estimation of the detected signal. We still have some scaling factors to do with the input intensity, but if we could calculate by some other means that the total probability of transmission is 1%, then we would have a predictor for our experiment. This is a slightly more complicated case, so not the cuvette with just a laser beam in and a laser beam out, but a geometry where we have a source and a detection fiber that are placed on a piece of tissue. So light is entering the tissue from on the left-hand side from the source fiber. Then it bounces around, it's scattered around in the tissue, and some of the light is picked up by the detection fiber. the idea is now if you want to calculate some or predict the signal that we would measure in this case, what we could do is just simulate the likelihood, the probability of all these individual paths that you see in this picture. So this is just a fraction of all the possible paths, but we could try to simulate as much as possible the likelihood that such a path happens. And if we can calculate them all, then we can add them up, and we can arrive at an answer that says, let's say that the probability is also 1%. So again, the total probability of photons of these billiard balls in this picture, the total probability of these photons traveling from the source fiber S to the detection fiber D is going to serve as an estimation of the signal that we will measure in the real experiment. So in order to do that, in order to calculate this total probability, we first have to calculate the probabilities of each possible photon path. Of course, we cannot do that, but we need to do as much as possible, calculate from as much as possible, and then we can add all these individual probabilities to find the total probability. So basically, the recipe for finding the probability of such a photon path is to break each individual photon path into a chain of sub-events, and that's again illustrated in the picture on the left. So we have a step where there is a propagation from injection point to scatterer number 1. So we can calculate what is the probability that the photon propagates without anything happening from injection point to point 1. Then we can calculate the probability that the photon is actually scattered there at that point. And then the probability that it is scattered into a certain direction. Once we have that, okay, we can calculate what is then the probability that it scatters to point number 2 over such a distance without anything happening. At that point, we need again to calculate the likelihood that the photon scatters from the direction 1 to 2 into the direction 2 to 3. Etc., etc., etc. So we have to build up this chain of probabilities of sub-events, which we are going to assume that are all statistically independent. So the probability of scattering into a certain angle is not going to depend on the distance that the photon, the billiard ball, traveled before that. Etc., etc., etc. So we get a sequence of probabilities of all the events that make up the photon path, which we assume are all going to be statistically independent of each other, so they will not depend on previous values. And in that case, we're allowed to multiply these to obtain the total probability of an event or of a photon path in this case. So again, here, what you see in this picture here is a possible photon path, and we can calculate how likely this path is going to happen just by calculating the individual probabilities of the steps that build up this photon path. We can multiply them if they are independent of each other, and then we will get the total probability of this event. And then the next step is we can do that for. Or we can try to do that. Let's put it that way. For any possible photon path that goes from the S to the D fiber, from A to B, from the source to the detector, and if we then again try to add all these photon path probabilities, then we will get the probability of the total signal, and that's going to be our measure for the signal. So basically, at this point, so this is the general approach. At this point, we can take two approaches. We can go to the right-hand side, and that's not what we're going to be doing today. But we could try to calculate it. We could try to make a model of these individual probabilities, and we could try to calculate all the maybe with some simplifications. But we could try to calculate all the probabilities of the individual steps, and then make drive an analytical expression for the total signal. That's not for now. What Monte Carlo simulations are about is to really try to use the computer to generate many of these photon paths, or simulate many of these photon paths, calculate their individual probabilities, and add these all together to find an estimation of the signal. So that is the goal that we want to do. So basically, this slide, and I'm not going to dwell on this one. This basically summarizes that again. So we have a detected signal, a probability. The detected signal is going to be proportional or measured or predicted by the total probability that photons that are launched at fiber A will be detected by the fiber at B. There are many possible paths that a photon can take to get from A to B. So we want to calculate the probabilities of all these possible paths and add them, and to calculate the probability of an individual path in this whole collection. We split up the path. We split up the process in propagation steps without anything happening, and then a scattering step where the direction is changed, and then again a propagation, and then again a scattering, etc., etc., etc. So that's how it's done. And again, what we're going to do now is use try to use that do that not find numerical expression, but use that do it in a computer. So there's basically two ways we can do that, and I want to start with a very practical one, which is related to numerical integration. So let's say we have a certain function is given by on the horizontal axis by some minimum value and some maximum value, x minus and x maximum, and correspondingly on the vertical axis we have a y that is f, the f of x minimum, and y that is the f of the function value of f maximum. So let's say we want to calculate the integral of this function. So very quickly, what is this integral? What does the area below the graph? Exactly. That is exactly the question that the answer that I was looking for. So it's the area under the curve. Okay. Now let's do some manipulations. Let's rescale the graph. So where the vertical axis is going to be, we're going to extract the minimum value on the y-axis, and then we're going to divide by the maximum minus the minimum. So that will ensure that the values on the vertical axis will range between 0 and 1. We can do the same thing for the horizontal axis. So we will we take the values of x, but we extract subtract the minimum and then divide by the maximum minus the minimum. And that also ensures that the coordinate on the horizontal axis will run from 0 to 1, like this. Basically, what we can do now is put a square around this, the square that has coordinates 0, 1, and 1, 0. If you would calculate the area of that square, it would be 1. And the area under the curve of this rescaled curve is going to be some value that is less than 1. Agreed? Okay. Okay. So now again, and this is very similar to the determination of pi that I've tried to explain last week. If we now just shoot random points onto this 1 by 1 square, then we'll see that some points fall below the curve and some points will fall above the curve, and we can estimate the area by just calculating the range, by calculating how the ratio of the number of points that fall below the curve divided by the number of points that we actually shoot in. So we can, and for each of these points, that means we draw a uniform on this axis. We draw a uniform random number between 0 and 1. That's what the computer does best. So you get something between 0 and 1, which is going to be the horizontal coordinate, the x coordinate. And a second, and we'll draw a second number that is going to represent the vertical coordinate, the y coordinate, also between 0 and 1. And we're just going to place that. If it is above the curve, I've labeled it red here. If it is below the curve, it is labeled green here. And the area under the curve is found then by calculating the ratio of the number of points below the curve over the total number of points that we actually shot in. And of course, if you want to really calculate the integral, then you have to scale back. We did this rescaling to have it between 0 and 1. If you really want to calculate the area, you have to rescale back. But this is a very simple way. If you have a very complicated formula that is very difficult to integrate analytically, this is a very simple way to numerically calculate the integral. Now, suppose this function that I just drew is a true probability density function. So it is a probability density function of some random variable x. Let's say an angle or a length or something like that. So one very quick question: what is the if I would calculate the integral from that function from the minimum value that it can take x min to the maximum value that it can take x max, what would be the value? That's a definition. It's not something that you can calculate. It is a definition. The definition that has to do with the probability density function. Yes, exactly, Sharon. No, Sharon is right. If x minus and x max are the span of the total domain, or the minimum and the maximum that the values of x can take, then the probability that x falls somewhere in between is going to be 1. You draw a random value. Calculate a random variable. It can only fall between x minus and x max. So the probability that it falls anywhere in between is going to be 1. So so this, in this case, this integral, this area on the curve has to be 1. Yep. So we can do the same rescaling for x if we have x minus and x max. So we can subtract the minimum value and we can divide again so that the horizontal axis is again scaled between 0 and 1. This is not going. Mix some here. Okay, so so let's say we one quick question, because I think there's a animation fault in my slide. It's always the same thing. Let's say we draw a we can now draw a uniform. So we did this rescaling, and we can now draw a uniform random number that represents a point on the horizontal axis. So x sub r and d is some location on the horizontal axis. So then the quick question is, what if I would calculate? Let's say I know the function, this true probability density function. What does p with argument x, r, and d actually represent? And again, I know probabilities are a little bit fake, so a fake answer is okay. Pepijn, was that an answer to my question now, or? Okay. Yeah, I'm sure it is. So any ideas? So so I would draw a random. So I've rescaled the horizontal axis so that it has values between 0 and 1, and then I have the computer generate a random number between 0 and 1. So I'm stuck with this one value. But I could calculate, if I know the function, I could calculate p or f of that x, r, and d. What does it represent? Yeah, okay. If it's discrete, then the probability, yeah. So it's a measure of the probability that this value actually happens. That this value of x r and d actually occurs. So let's say that the probability of this drawn x r and d is 25%, 0.25. That would mean that if I would draw this x r and d values 100 of times, then 25 times out of that that would be a random value that actually goes into the distribution, and 75% of the times it would be a random value that is not that should be rejected. That's not useful. If the probability is much higher, if this is 0.6, then from every 100 draws I would keep 60%, and I would reject 40%, 40 of them. And so this basically is what the so-called acceptance rejection method of Monte Carlo sampling does. So let's say by some magic or by some tweaking of my computer, I draw the same random number for x many times. I can draw a second random number that describes the y coordinate, just as I did with the as we did with the stochastic integration. If I know I can calculate the value of p of that random number x r and d1. If that value falls below the curve, then I accept the number. If it falls above the curve, then I reject it. So again, I will draw a uniform random number between 0 and 1 that represents a point on the horizontal axis called x r and d. I draw a second uniform random number to represent a point on the vertical axis called y r and d. And then my algorithm is if y r and d is less, so that would correspond to the green point, is smaller than the value of the function for x r and d. So that means that the xy point now falls below the curve. Then I would accept it, and then I would accept x r and d as a random variable, as a random value in my set. If it is larger than p as a function of x r and d, then I would reject it, and I would just have to try again. So this will give me a sequence of accepted random values. So I only accept them when this condition is met. If this condition is not met, then I will reject them, and I will have to try again. And if I have now this sequence of random numbers, if I then calculate if you would then calculate the histogram of these random numbers, then we'll see that it corresponds to the input, to the original probability distribution function. Is this approach clear? Can you also so it's extremely straightforward. You just draw two random numbers. You know the function. You're just going to check, is it below the curve or above the curve? If it's below, accept it. If it's above, reject it. So what would be the drawback? Yeah, computational time is going to be a problem. So let's say you have a function that decays a little bit like this one here. Let's say you have a function that decays exponentially. The random numbers that you draw on the vertical axis have to be between 0 and the maximum value of the function of y. So that means that if you would draw a random number on the horizontal axis that is close to 1, so on the right hand side of this graph, then most of them would simply be rejected. So you have to try many times. You have to generate many random numbers before one is actually accepted for that. So the computational time can be very long. I had a short assignment for that, but I'm just having a quick look at the time. So I think I'm gonna once again change this into a homework question. But basically, the question here is, okay, let's take a phase function, in this case, the Rayleigh phase function, and use this acceptance rejection method to sample the phase function. And just as a teaser, the graph here shows my implementation. So the blue line is the true phase function, the true implementation, and the red points are generated randomly generated values that occur using this method. But I'll turn this. I'll not give you the answers. Turn this into a homework question at some point. Okay, we've seen this. So again, to calculate the detected signal, we're going to calculate first the probability of any given path, and then which we find by. You're very sharp. Yes. Yes, but I'm not going to go into that. For both the BMO and the LTI, we're gonna talk a little bit more about Monte Carlos in one of the upcoming classes, and then what we'll then see is that just very quick, that P, the joint probability density function P of theta and phi was 3/16 pi times 1 plus cosine squared theta. But marginal, if you split them up in probabilities for theta and phi separately, then for theta it's going to be 3/8. Okay, super. But we'll get to that later. Exactly. Yeah, because 2 pi the phi is sampled uniformly, so that's going to have a probability density function that is 1/2 pi, and then the other part is about theta. Okay, so let's take a look again to the cuvette. Suppose that PA, a number PA, just a pure number, is the probability of absorption of an absorption event per unit length along a photon path. In this case, the photon in the top picture, the photon path is really simple. That is just a straight line through the cuvette. But if you want to make it a little bit more complicated, then we can have this situation on the bottom where a photon path can be very convoluted. But suppose that PA, the number PA, is the probability of absorption per unit length along a photon path. So then PA times a very small fraction dl, so allowing for the fact that PA can change as a function of length, but that's making it a little bit more complicated. But PL times dl is the probability of an absorption event of absorption of the photon between L, location L, and L plus dl. So PA was a probability density. It had a unit, the probability per unit length. If you multiply that with dl, which is a length, then you get a pure number. Then you get basically a probability of absorption between L and L plus dl. That also means that P of L, PA of L, is the probability density function of a free path length. So the probability that is related to the free path length that the photon can take. If it is a true probability density function, it is going to be normalized. So if you integrate PA of L over dl, then the answer has to be 1, because the absorption event is going to take place at some point, anywhere. In this case, anywhere between the possible values, not for the cuvette, but for an infinite medium, the possible values are somewhere between 0 and infinity. There is going to be an absorption event. So if you integrate this PA of L times dl from 0 to infinity, then the answer has to be 1. But now assume that P of L is a constant. PA times dl, the constant PA times dl, is the probability of absorption in an interval DL. Because now there is no, because it is a pure number now, so it really does not matter anymore what L is. So PLDL then represents the probability of absorption taking place in an interval DL. So quick question, what is then 1 minus PADL? Almost. Yeah, transmission, yeah. Transmission through. No, not exactly through the QF, but through yeah, through the L. So basically, it is the probability of not absorbing in an interval DL. So transmissions, I mean, combining all your answers, you have it right. It's the probability of transmitting through an interval DL. Now let's say I stack a few of these intervals together. So what would then be 1 minus PADL times 1 minus PADL? Let's say we stack 2 of these intervals together. So if 1 minus PADL is the probability of transmission through an interval DL. So what Sharon says is right. The probability that isn't absorbed in either interval. So it's not about an area. It's along a length. Theoretic, and Vlad also is right. It's the probability of not absorbing in the interval 2 times DL. So it is basically an expression of you can calculate the probability of an event or a non-event in this case, and then calculate the probability of that same non-event in a sequence after that. And if they are unrelated, if they are statistically independent, you can just multiply these probabilities to find the total probability. Yeah. So 1 minus PADL times 1 minus PADL is the probability of no absorption at all in an interval 2 times DL. Now, of course, we can, and again, the caveat that it only works if these events are uncorrelated, but we will be assuming that all the time. So now take a longer path length L. So the same definitions. We have PA as the probability of absorption per unit length. We have PADL as the probability of absorption in an interval DL. And we had 1 minus PADL as the probability of no absorption at all, also in that same interval. Now let's break a longer path into n smaller segments, all of length DL. So then the question is, what is the probability of no absorption between L and between 0? That should be, what is the probability of not absorption between 0 and a length L is n times DL? Yes, I see the answer already coming along in the chat. You just multiply them out. So for two segments it was squared. For 3 segments it will be to the 3rd power, and then for n segments, if you split it into n segments, it will be to the nth power. So the total probability is going to be 1 minus PADL to the power of n. Okay, now let's make some mathematical fun. We can take the natural logarithm of both sides of this equation. So we can calculate ln p, and we can calculate the natural logarithm of the term on the right-hand side. And as you know, that means that the n, the power of n, just ends up in front of the natural logarithm. Okay, now the second step. Now let's assume that the probability of absorption is really, really low. Or actually, let's assume that the product of PA times DL is really, really low. And we can always assure that because we can take DL as small as we like. So we can always assure that PA times DL is a very small number. And that means that we can approximate ln 1 minus PADL with simply minus PADL. So then we have the, and I'm leaving the approximation there just to be sure. We have the equation ln of the probability, the natural logarithm of the probability, is approximately equal to n times minus PADL. Now we can exponentiate again. So take the exponential again. We have on the left-hand side we have p back again. Exponential of the natural logarithm just cancels it. So we have the probability again, and then it's going to be exponential. Looking at the right-hand side of minus PA times NDL. And NDL we already had because we chopped up a path length of length L into n sections DL. So the product of NDL just gives us back L again. And this basically is again a new, or again a manifestation of Lambert-Beer's law. So what we calculated now was the probability of transmitting through a cuvette, which of course we already had before. That was Lambert-Beer's law. So if we calculate these two, if you compare these two equations, so the probability that we calculated is going to be a measure of the experiment that we do. The experiment was given by Lambert-Beer's law. I over I0 is exponential minus mu A times L. So if we compare these two, then we see that mu A is the same as this PA that we loosely defined earlier on. So the absorption coefficient is just the probability of absorption per unit length. And also unit-wise that matches because the absorption coefficient had units of per meter. So just Lambert-Beer's law again. That means that let's say the likelihood of transmission is so if we that means that we normalize on the input intensity. The likelihood of transmission is going to be exponential minus mu A times L. We had PA previously, but now we know that that is equal to the absorption coefficient mu A, so we can just fill that in. Then the probability of not transmission in the cuvette. So the likelihood of transmission is going to be given by e to exponential minus mu A times L, and the probability of not transmission, which means absorption, not transmission is absorption. So the probability of absorption is going to be given by, over the whole cuvette, is going to be given by 1 minus that. So 1 minus exponential minus mu A times L. And again, this is, we were evaluating probabilities at the end of the cuvette. So what we basically calculated now with this last expression is the total probability of absorption somewhere inside the cuvette. So formally, that would be a CDF, a continuous distribution function. Correct? It's going a little bit fast, I realize. So this is a cumulative distribution function that describes the total probability of absorption over a distance L, so the length of the cuvette, or less. So somewhere between 0 and L, there's this describes the probability of the absorption coefficient. And I tried to use as much as possible the capital values for the cumulative distribution function and the lowercase values for the probability density function. So that is one way, one hint to see what we're talking about. Of course, they are related again by this integral relation. So the cumulative distribution function was the added up probabilities of absorption happening in this case between 0 and L. So that means that this cumulative distribution function is related to the probability density function by the integral from 0 to L, the domain of the variable that we have now, of p, well, L prime d L prime, just to make it clear that the integration boundaries run from 0 to L. So L prime is in this case a dummy variable. And it also means that we can find the probability density function by differentiating this equation. We can just differentiate the integral out and then find the likelihood of absorption per unit length. And then this expression This expression remains. So P of L, small p, lowercase p of L is mu a times exponential minus mu a times L. And I'll leave it to you to actually, if you actually calculate this integration. So if you would calculate the integral of PL over all possible values of the path length, so that would be between 0 and infinity, then this integration would yield a value of 1. So you can check the normalization. All right. So let's summarize this. So this is a probabilistic meaning of the absorption coefficient. So mu a times dl, we had PA before, we now have mu a, is because it equated to Lambert-Beer's law, is the probability of absorption in an interval dl. The function lowercase pl is equal to mu a times exponential minus mu a times L, has units per meter, is the probability density function of a absorption-free path length of a photon. So the probability that the photon travels a length L before it is being absorbed. Then PLDL, if you multiply that with the small segment DL, is the probability, basically, by the same definition, of finding a free path length until an absorption event occurs in the interval between L and DL. So that basically cancels out the units. And then we had, now in green and with the capital P, the cumulative distribution function that gives the probability that the free path length until absorption lies in an interval between 0 and L. Or, turning that around, that the photon is absorbed somewhere between 0 and L. Then one quick question, and I already saw it in the comments. Can you now calculate the expected value or the mean? Do you know now what the expected value or the mean value of the free path length is? So taking the second equation on this slide, the probability density function for free path length, how? So if you know the answer, that is fine. But if you can give me the approach, that would be great. So again, this question boils down to how do you calculate the expectation value of some random value variable if you know the probability density function. So if I scroll back in the chat, think. Somewhere here. Yeah, you read it. Yeah. You have it again. Yeah. So you multiply you multiply the variable itself with the probability density function, and then calculate the integral over that whole domain. So in this case, what you would need to do is calculate the integral of L times P of L. So again, the second equation that is on this slide, L times PL, and then evaluate that. Yeah, I'm sorry, I've written it here for scattering, but for the interpretation for absorption is the same. So mu(s) times or mu(a) times dl is the probability of scattering or absorption in an interval dl. If you normalize that using or if by the derivation that we did before, we can find that PL is P of L, the probability density function of free path length is mu(s) times exponential minus mu(s) times L, or of mu(a). The probability density function for a free path length L until a scattering or an absorption event occurs. And if you do the calculation, so L, multiply L with PL and then integrate from 0 to infinity, then you'll find that the average path length is 1 over mu(s). If you do it for absorption, it is 1 over mu(a). mu(s) and mu(a) had units of per meter, so 1 over mu(s) or 1 over mu(a) have units of meters, so that actually is length. So this average length is the mean free path length between the scattering events or between absorption events. So this is the mean length that the photon travels between being scattered again or being absorbed. Of course, for absorption, it is a little bit difficult to interpret this because once it's absorbed, it's gone. But the statistics are the same. So that's why for scattering, it is a little bit more clear. So that is one extra parameter and one extra interpretation of the absorption and scattering coefficient, the probabilistic meaning of absorption and scattering coefficient, the mean free path between these events. And then the cumulative distribution function, so 1 minus exponential mu(a) or mu(s) times L is the probability that the free path length lies in the interval between 0 and L. All right. Just a quick look at the time. Are you still up to this, or do you want a small break? I think you need a small break. Let's take a tiny break. Yeah, let's take if you're okay with that, let's take a 5-minute break, and then I'm gonna just reorganize because it looks like I have 20 slides left. That's not gonna happen in 50 minutes. So I'm gonna just rearrange my slides a little bit, and then we'll do 15 minutes more, and after that Johannes takes over, and then I'll put the rest into our respective classes. That is fine. Okay, so I'm going to stop the recording and stop the slide sharing now, and then I'll see you in 5 minutes.